So, in order to properly evaluate this integral, if we were to do it in the Cartesian plane, it would be very difficult. But luckily, we can convert it into polar coordinates. And there's two hints that we can do this easily. The first is that inside the integral, we have x squared plus y squared, which is the equation of a circle of radius r. And in the x bounds of the x integral, we have x equals plus or minus square root 4 minus y squared, which becomes x squared plus y squared equals 2 squared. So what we're looking at here is a circle of radius 2. And in the y bounds, it's going from 0 to 2, which tells us that it's only the positive half of this circle. So we can easily draw this, which will give us a better idea of the double integral we have to set up. It is the top half of the circle of radius 2. Now that we have that graphed out, it's much easier to set up our double integral. So it would be from 0 to pi, because it's the top half of the circle. It's radius 2, starting at the origin. And then x squared plus y squared becomes r squared. And dx dy becomes r dr d theta. Simplified, this is 0 to pi, 0 to 2, r5 dr d theta. So now this is in a form that we can easily integrate. So first we'll take the integral of the radius, which will be r6 over 6 from 0 to 2, which turns out to be 32 over 3. And then we can take the integral of the outside. So it would be 32 over 3 theta from 0 to pi, which turns out to just be 32 pi over 3. Very easy to solve once it is converted to polar coordinates.